All right. Okay, cool. Let's go ahead and get started. Everyone on Zoom, you guys can hear me okay? Perfect. All right. So, yeah, if you're here in person, thank you for braving the snow and ice to be here. If you're here online, welcome. Um, cool. So, today's an exciting day because it is the last lecture where we're going to be focusing on coding and visualizing some sort of pattern. We've spent two lectures that have really been focused on this, and for the next lecture, the last lecture, we're going to step away from some of the blackboarding and coding in order to talk about more broad visualizations that we can make using everything that you've learned from this course. Some of these softer skills that I've learned pursuing generative art for a little while, and I'll be hopefully passing that on to you so you don't fall into some of the same holes that I did the first time I was going through this process. That being said, we do have a bunch of fun stuff for today. So let me go ahead and share my screen and we can go ahead and get started. Okay, so today we're going to be talking about mazes. And mazes are really, really fun. They're interesting to code out. They're interesting to solve. We'll talk about their relationship to nature. We've been focusing a lot on patterns in nature. Whoops. We've been focusing a lot on patterns in nature. And this one's a little bit different than our usual. So we'll do 3 quick slides, and then we'll get into talking about how maze generation works, and then we'll actually go ahead and code out our very own mazes. So a quick note, if you guys have been following along with the syllabus, today's lecture was entitled, I think, Losing Your Way and Finding Your Way Out, and we said we would be both generating mazes and solving them. Just for the sake of time, and because I really want to go a little bit slower with the content today, we won't be doing any maze solving algorithms, but rest assured, if you understand how we create these mazes, it is very, very straightforward to write the code to then solve the mazes. So we might add that in as like an assignment at the very end of this lecture. Okay, so let's start by talking a little bit about mazes and labyrinths. The first thing that might have stood out to you is that mazes, unlike everything else that we've talked about, aren't supernatural, right? They aren't something that you go out and you see all the time, at least not unless you're willing to squint really, really hard. Maybe if you look at a patch of trees from overhead, you can see a maze-like structure. If you are in a cornfield, maybe you see a maze-like structure. But mazes and labyrinths, especially the way that we think about them and talk about them colloquially, we don't see that in nature very, very much. That being said, we do want to talk about them for lecture because despite them not being a natural pattern, the tools that we use in order to create mazes build off of a lot of the tools that we use in order to create the natural patterns that we've talked about so far. So the toolkit is very similar. And I think it's also important that we cover mazes because they help us understand how to take some of the skills that we've used in visualizing natural patterns and apply them to new patterns. So if maybe your interest isn't so much in visualizing natural patterns, it's in something else, I think this is a good medium to do so. And the last reason that we want to talk about mazes and labyrinths is because in a way, they are not an important part of, I guess, like nature, but they are an important part, an interesting part of human history. Mazes and labyrinths have been a subject of interest across time, cultures, religions. It has different meanings depending on how you view them spiritually. And so I also wanted to investigate that side of things. So you might be familiar with labyrinths through Greek mythology. We had King Minos and the labyrinth with the Minotaur in it, and Theseus famously killed the Minotaur, and he had like a ball of yarn that he used in order to find his way across the labyrinth. And so we see mentions of labyrinths and mazes in Greek mythology. But we also see them, very far back in Indian history. In Goa, they had a lot of carvings of labyrinths that looked very similar to the ones that we saw in Greek mythology. And you'll see that labyrinths and mazes show up all the time throughout Europe in like the 17th and 18th centuries. They're really, really interesting, and they've been investigated by a lot of people. They also have like interesting spiritual meaning. If you look at the spirituality of mazes throughout time, a lot of the time mazes are considered good and spiritual because they sort of walk you through this path or this journey that is non-linear, and it has implications for time being non-linear and thinking of things through a new perspective. But mazes have also been considered evil in a lot of different circumstances. Another interesting connection to India is that a lot of the times mazes have been considered evil in some writings because they are a place for tricksters. They can also be considered evil, and I think they are in either Greek or Roman mythology, because they are a place that you can very easily get lost and never get found. I think there's some mythology related to mazes and sailors as well. And so mazes are really, really cool. They're really, really interesting and have been to a lot of people over time. Now, there's also a lot of interesting modern representations of mazes and labyrinths. The first one that might come to mind is Relativity, which you can see on the bottom right there by M.C. Escher. And this isn't a strict maze or a strict labyrinth, but it is a really, really cool depiction of what mazes and labyrinths could look like. If that's not your thing, if you're more into horror movies, The Shining is an incredible book and movie by Stephen King, in which they have in the Overlook Hotel a maze, a hedge maze, right outside of the hotel, which you can see over on the bottom left there. Okay, so mazes and labyrinths, pretty cool, pretty interesting, and lots of good reasons to visualize them. Let's talk a little bit about how we create mazes and labyrinths. So the first thing that we'll talk about is cellular automata being used to create mazes. So for everybody that was here for lecture 4, we talked a little bit about cellular automata, and the idea really was just that we have some sort of grid that consists of cells. These cells have a state that is a function of its neighbors. It's a function of the state of the cells around it. And by inducing some rules upon how these states change, we get interesting global behavior. And this was cool to us in the last lecture, because not only could we visualize things like Conway's Game of Life, which we talked pretty substantially about, but we were also able to use rules to visualize things like fractals, which we covered 2 lectures ago. And so there's lots and lots of connections between all of this stuff. That's also something that we'll cover in the last lecture. But as it turns out, a cellular automata can be used to create mazes. And this isn't going to be the focus of today's lecture, and I'll tell you why in just a second. But it turns out that the cellular automata mazes that we can create are very, very similar to the rules that are needed to produce Conway's Game of Life. In fact, we use only 2 very small modifications to those rules in order to create a cellular automata that generates maze-like structures. And that is that's really, really interesting, that connection there. Now, as I mentioned before, these aren't going to be the focus of today's conversation, and the reason is that the structures that are created using cellular automata are maze-like. They're not colloquially what we might think of as mazes. Just like in nature, you really have to squint, and then they become mazes. And so what you'll see with the cellular automata mazes that we create, there's not a defined endpoint or a start point. There's like no exits. There are some places that are impossible to get to. There's some parts of the maze that are really trivial. And so we don't want all of these characteristics when we visualize traditional mazes, but we do get them when we see mazes in the natural world or with cellular automata. Now, interestingly, there has been a little bit of work done to use cellular automata to create real mazes. If that's of interest to anyone, I have a link there to a paper, and I'll get these slides posted soon. Okay, so this is cellular automata for maze generation. What we really want to spend the vast majority of today focusing on is perfect mazes. And this is a little bit more like colloquially close to what you might think of when we say the word maze. The idea is that they are not natural, but there is only one solution from a defined like in part to the maze to a defined like exit part of the maze. And there are no inaccessible areas. So it doesn't make sense for us to have a part of the maze that you can never get into and never get out of. Well, really never get into is the main bit, because that makes that part of the maze completely useless. And so as it turns out, we can generate these perfect mazes in all sorts of interesting ways. We can use recursive algorithms or iterative algorithms, and this will be something that we talk about in a lot more detail because it makes a big difference when it comes to the way we create generative art or visualizations of these mazes. And we can use a variety of different techniques. We can use graph algorithms, so if you're familiar with Prim's and Kruskal's algorithm from Data Structures and Algorithms courses, we can use those in a randomized fashion to create perfect mazes. We can also use things like tessellation, and perhaps most interestingly, the random walks that we talked about in that very, very first lecture before we knew basically anything about generative art or using computer science to create natural patterns. Those random walks too can be used to create perfect mazes if you create a couple of modifications to our random walker object. Okay, so that's everything that we'll talk about in terms of slides for today. The roadmap for the rest of lecture is we're going to take a quick look at modifying the Conway's Game of Life algorithm that we wrote last lecture to create cellular automata mazes. And that'll be really, really quick, just a couple of minutes. And then we'll spend the vast majority of today's lecture creating perfect mazes. And I know we focus a lot on the coding aspect of things. Today, I want to take a step back and really focus on the whiteboarding. And once we understand that whiteboarding, I think coding out this maze is going to be a very, very simple process. Okay, so let's start with cellular automata mazes. Let's go back to this slide right here. So we said that in order to create a maze using cellular automata, we need to change two rules. The first rule is, in Conway's game, we said a cell was dead due to underpopulation if it was previously alive, and then in the next generation, it had 0 or 1 neighbors. We want to drop that requirement to just 0 neighbors. A cell only dies if it's all by itself. And then we said the overpopulation requirement is that if a cell has 5 neighbors or more, this really should be 5 plus neighbors, it dies due to overpopulation, and that's a step up from our 4 plus neighbors in Conway's game. And so to show you guys what that process looks like, and really this is also to emphasize just how modular the code that we develop is, this is the exact code that we wrote in order to simulate Conway's Game of Life in Lecture 4. If I run it, you'll see that as soon as I press the P button for play and pause, we have Conway's Game of Life running, just as we're used to. And again, maybe if you can squint here, you can see a little bit of a maze forming, but not really. So let's go ahead and modify Conway's game. Remember that we applied all of our rules in these set of little if statements here, and so as long as we change those rules here, everything else should work as intended. So we want to say that underpopulation kills a cell only if the number of neighbors is less than 1, right? Only if you have 0 neighbors do you die due to underpopulation. Otherwise, you die due to overpopulation only if you have more than 5 neighbors. And so we'll just change those two rules here. We'll go ahead and run our CA maze. And then once I play it back to you, you'll see that in one generation, it's created something that sort of looks like a maze. And again, I say sort of looks like a maze because looking at this, you can't really tell where the in and out portions are. But it's a lot easier to see this pattern and say, hey, there's something that looks like a maze. Now, this isn't all that interesting to us because it turns out that this process creates this maze-like structure within one generation. There's no like generation visual that we see with this. And so for that reason, it's not all that interesting visually, but it turns out that it becomes a lot more interesting if we don't randomly fill in the entire grid, but instead if we only fill in something like the center of our grid with randomly placed alive and dead cells. If we do that, then what happens is our cellular automata grows our maze, and we can see that growing process happen in real time. And so we'll take a look at how we can modify our existing code in order to create that process. So really what I want is instead of when I play this for the first time, when I run this, instead of every single cell having an equal probability of being true or false, dead or alive, we only want the center of this maze to be filled with cells that are randomly dead or alive. Everything outside of that center should be entirely dead always, and they will eventually get filled in by our cellular automata. And so the way that we can do this, right, is we go up to our setup code. Right now, at every single point, we're saying it has equal probability of being true or false. Maybe we only want to focus on the middle cells. And so maybe we don't want to start our I out at 0. Maybe we want to start it out closer to the middle. So maybe we want to start it a fourth of the way through. So 1/4 of the way through. So 1/4 times n. And we should have a float in there, or actually we don't. We can just do n/4. That's just as easy. And then we don't want it to go all the way to n, right? We don't want it to go all the way to the end. We want to stop it maybe at 3/4 of the way through. So maybe we can stop it at 3 times n/4. And we want the exact same for the j values. Are there any questions about what I'm doing here? Okay, so if this works properly, what we should see, right, is that we only have this inner square filled in randomly with cells. And what happens when we play this is you'll see we randomly are allowing ourselves to move and create this maze-like structure outside. And it's not all that interesting when we have just 30 cells, so maybe we increase this to something like 100, and I'll take our stroke weight down just a little so that we can really see where everything is. Okay, so this is nice. Let's go ahead and run this. And that's going to create a really, really interesting maze-like structure. And so very last thing that we'll do before we move on is, in the spirit of this being generative art and us having infinite possibilities, let's say whenever our key is pressed, right now we're switching between playing and pausing. Now I want to say if this key is the letter P, then we'll toggle between playing and pausing. But if the key that I press is R, then I want to reset and I want to restart my process from scratch, just so that I don't have to click that run button every time I want to do that. And so the way that I can do this is just recalling our setup method. Remember, our setup method is called at the very beginning when we open our canvas. And so calling our setup method once more will reset everything. And so if we run this again, we'll go ahead and press the play button. And it's really cool. This animation is finished. So if I press the R button now, we get a completely new maze, and we can run that. And so we can repeat this process over and over to your heart's content until we find a maze-like structure that is interesting or unique or that you think has cool properties, and then investigate that very, very quickly. And I'm sure, as you guys can probably already tell, the possibilities here are endless. There's lots that you can play with in terms of the color, creating animations, just really, really interesting stuff all around. But we'll stop our conversation about cellular automata and mazes there. And I'll pause if anyone has any questions. Okay. So what we want to focus the rest of our conversation on today is going to be how we create perfect mazes. And this is going to take a little bit of setting up context. So the way that we want to create perfect mazes for this specific lecture is going to be through a very simple process called randomized depth first search. So for those of you that have a computer science background, the words depth first search should be very, very clear to you. You probably already know exactly what a depth first search is, and you probably have coded out a DFS in the past. That randomized bit might be a little bit new to you. If you haven't heard of a DFS, it is a recursive process of searching through some sort of data structure, generally looking for like an element of something. And so again, as with everything in this class, we are going to be using one specific algorithm and creating one specific visualization, but a lot of the other algorithms for maze generation build off the same principles of recursion and backtracking that we'll be talking about today. And so if you find a different algorithm that interests you, you should be able to use what you've learned here in order to code it out. Okay, so let's talk randomized DFS. How does this thing work? Well, before we get to exactly how the algorithm works, I want to talk to you guys about how mazes in general might be created programmatically. And there are really two sort of like big paradigms here. There are two big ideas for how we can create these mazes. The first paradigm is very constructive. It says, all right, let's start out with nothing. Let's just start out with a box, and we will create walls that make this some sort of maze. And we will place these walls at locations that make this maze interesting, and you eventually find your own solution to that maze. And that's the sort of constructive process of maze creation. Now, the second process of maze creation, the one that we'll be focusing on today, is just a little bit different. It's going to be destructive. And so the idea, once more, is that we have a square canvas, but this time, instead of starting out with nothing inside our canvas, let's start our canvas out as a grid. And then we will select walls in our grid to remove strategically such that this turns into a maze. And so maybe we remove this wall right here, and then maybe remove this wall right here, and then this one right here, this one right here, this one right here, this one right here, and then maybe this one right here, right? And so we have a very simple maze here. This isn't very difficult to solve. If we say, this is the exit, this is the entrance, it's very clear that we want to do this, and we have a maze. But these two paradigms are going to be really interesting because generally when we have most traditional maze generation algorithms, they're going to follow either of these two paradigms. Now, the reason that we'll be talking about this second paradigm is because not only is that what naturally makes sense with a randomized depth-first search, but we've also talked a lot in this class about how to create grids, how to manipulate grids, and so some of the code that we look at with grid creation should look relatively familiar to you to begin with. Okay, so we want to use a destructive process. How do we want that destructive process to work? Well, with our like sort of backtracking, randomized depth-first search approach, the way that it works is going to be relatively straightforward. So let me go ahead and create a new grid for you guys. So the way this works, and I'll be using 3x3 grids whenever we draw them out on the board. It's not going to result in very interesting looking mazes, but it will be nice just for the sake of simplicity. So the way that our randomized DFS algorithm works is we want to choose a start point. And interestingly enough, we don't choose an endpoint. That endpoint is figured out through the algorithm. And so we start out here, and we want to say, all right, let's look at all of our neighbors. And we're going to think only 4 directionally here. It would be very interesting for you to think 8 directionally about neighbors on diagonals. And maybe we can consider that for the assignment. But for now, let's only think 4 directionally. And so the question that we want to ask ourselves is, have I visited this neighbor? And if I haven't, then I want to visit it. And so I'll ask myself, hey, have I visited my top neighbor? Well, they don't exist. Have I visited my left neighbor? Well, they don't exist. Have I visited my bottom neighbor? Well, no, I haven't. And so this is where the recursive step comes in. If I come to a neighbor that I haven't yet visited, then I want to delete the wall between me and them. And then I want to repeat this process on that next cell that I just removed the wall to. And so if I'm here, I want to ask myself, hey, have I visited my neighbor up there? Yes, I have. Have I visited my neighbor right here? Yes, I have. Have I visited my neighbor down here? No, I have not. And so I will open up this wall and visit this cell. Now, so far, I've been going through the same process for checking the same order for checking which of my neighbors comes next in this checking process. I've been checking north, then west, then south, then east. Here's where the randomized part comes in. If I randomize the directions that I check, if I randomize the directions in which I check the neighbors, then I'm going to get a really pretty maze. If I don't do that, if I keep with this same process of saying, do I have a neighbor up here? No. Do I have a neighbor here? No. Do I have a neighbor down here? Yes, let's visit, so on and so forth, then what you'll see if I go through this process is already visited this guy, nothing over here, nothing over here. I have to open up a place here. And then if I use the same process again, I will go upwards, right? I'll open up this wall right here. I'll open up this wall right here. This one, this one, this one. And I won't get a very interesting maze. I'll just have a maze that looks a little bit like a snake pattern. And that's what you'll see even when you scale this thing up. And so the reason that we want to randomize this process of choosing neighbors is we want to create interesting twists and turns in our maze, and that's how we achieve those twists and turns. And so here, I don't really have a choice. I have to move over here, right? That's the only 4 directionally connected neighbor that I haven't visited. So I'll go there and repeat this process. And now instead of starting at the top, maybe I go over here to the right to this neighbor. And so I delete my wall between myself and this neighbor. And I recursively start this process right here on this cell. Maybe here, well, I don't really have a choice. I have to go up right here. And then from here, maybe instead of going up, I move to the left. And I go right here. From here, I don't have a choice. I have to go up. So I go right here. And then from here, again, I don't have a choice. I have to move to the right. And so I go there. And now that I'm here, every single one of my 4 directionally connected neighbors has either been visited or doesn't exist, right? These 2 values don't exist. These 2 have been visited. And so that's the end of my recursive call there. I'm done with this recursion on this cell because all of these neighbors have been visited. So I move back to the recursive call here. All of these neighbors have been visited, right? This is where I started out. So this has already been visited at some point during my function. And so all of my neighbors here have been visited, move back here, all of my neighbors here have been visited, so on and so forth, until I have my final maze, which looks like this. So this might be the exit, this might be the entrance. Again, like I said, this is not generating a very difficult maze, but when we scale this process up, the mazes will get a lot more complicated. Is everybody cool with that recursive idea that we're implementing here? Okay, perfect. So we want to actually turn this recursive function into an iterative function. And the reason that we want to do that has nothing to do with the computer science behind it. Yes, it's absolutely true that if we stick with this recursive function, we can get a Stack Overflow error. And indeed, just to test out what would happen in processing, if I coded this exact same thing out, I did last night, and I got up to a 200 by 200 grid or 150 by 150 grid before I got a Stack Overflow error. But that's not why we want to use an iterative version of this algorithm instead of a recursive version. The real reason is in how interesting we can make our visualization. And so in processing, whenever we use a recursive function, my understanding is that, especially with stuff like this, it's very difficult to draw to our canvas between those recursive calls. And it's a lot easier if we instead convert this recursive process into a function that goes step by step, and then we can do what we've always done throughout this course, which is display, update, display, update, display, update. And the reason that doesn't work, right, when we use a recursive function is because by virtue of being a recursive function, if we want to display and then we update, that depth first search call, that recursive call, is going to go through and make our entire maze before it finishes, goes all the way back up the call stack, and ends that function, and then we display again. And so the process would be display, make the entire maze, and then display that, which is of course not what we want. We want display, make a little bit of the maze, display, make a little bit of the maze, display, and so we see the process of the maze being created.
A quick question.
Yes.
If this process is going to hit the end, so the solution, it changes direction, right? So it doesn't like solve it early?
What do you mean changes direction?
Like on the last example, it could have just gotten to the end by choosing the shortest path, but by like digging those walls down. But it chose not to do that, right? Because then that would make the maze not as complicated.
Right. Okay. Yeah. So that's true. But when you say shortest path, that implies that we already know where we want the exit to be, right?
Mm-hmm.
In this case, we didn't.
So you're putting the exit at the end after, not first.
We are putting the exit at the end, not first. Can you explain what you mean by that?
Like we create our maze, and then we choose wherever it ends up.
Yes, exactly.
Yeah, and
right.
That makes.
Yeah, so if we don't know where it ends up to begin with, I don't think we can do like a shortest path between those two. And if we did, then it wouldn't be a perfect maze because there'd be a lot of places within the maze that are inaccessible, right? By virtue of them being too far away and them not being like a practical way of getting from beginning to end.
Yeah.
So yeah, that's why we, I guess your initial question was, why don't we go back? Or maybe you can remind me what your initial question was?
Yeah, my understanding is for this recursive depth first search that you just keep on going one direction until you can't go that direction and then you change. Is that correct?
That is not correct. That's close. We don't want to keep going in the same direction. We want to randomize that direction, right? For the same reason that I talked about earlier, where if you kept going in the same direction and then just turned, you would get a very like simple, uninteresting maze.
Okay, cool.
Cool. Okay, awesome. So any other questions before we talk about taking this recursive algorithm and converting it to like an iterative step-by-step updating function? Perfect. Okay, so if we want to take this recursive process and make it iterative, we know that really what's happening behind the scenes with a lot of recursive functions is we're just adding calls to our stack frame, and we can use a stack to simulate recursion. Right? And so the way that we can approach this process is instead of saying, all right, start like at some start point and then recursively find your way all the way to the end. Let's use a stack and let's figure out a way that just breaks down one wall and then finishes. And then the next time we call this function, it'll break down the next wall and then return. And that's useful to us because we can use that as a part of our draw function in order to remove walls one by one and make this generation visual really, really clear. So the way that we want to do this is we want to keep track of which cell we're on currently, of course, but we also want to keep track of all of the cells that we visited in the past. Remember, the way that we did this recursion was we went all the way to the end here, and then we asked ourselves, okay, we're done with this cell. Now, does this cell have any outstanding neighbors that we still need to go to? And by virtue of this being a 3x3 grid, it wasn't very interesting because we didn't have any other cells that we needed to visit for any of these after their first recursive call. But for a bigger grid, we very well might. And so we need to keep track of not only our current position, but all of the previous places that we visited that might still be in progress. And we need to keep them in the order that we visited them, and that's going to be the utility of our stack. Everybody following me so far with the stack idea? And if it doesn't make a ton of sense to you, that's totally okay. We're going to draw out, just like we did with this recursive example, how the iterative example works, and we'll talk about that before we begin any of the coding there. Okay, so we have this stack filled with our cells. Now we want to choose exactly one cell for our next cell, and we want to break down the wall. And so let me move this up. And so maybe the way that we do this is, once again, maybe this time, just to make it interesting, let's do a 4x4 grid. Let's say we have a running stack over on this side. If you're unfamiliar with stacks, I know we have some new programmers here. The idea behind a stack is super simple. It's a data structure where you can access only the topmost element, and you can either add an element to the top of your stack, look at the topmost element, or remove your topmost element. Think of it as like a stack of books or a stack of cards, where you can always, like if you want to get to an element that is lower in the stack, you first have to go through all of the elements on top of it. And so it is last in, first out structure, where the last item that you put in is the first item out. Super accessible if you want to look up stuff about stacks. But the idea, right, that we want to use is we'll start at some location, and that'll be here, and maybe I'll go ahead and number our grid. So maybe we start at 0.00, and then we want to randomly choose one of the next neighbors to go to. And maybe here we choose the position 0, 1. And so we want to say, okay, let's break down the wall between 0, 0 and 0, 1. And now we want to consider what would happen if we started at 0, 1. And so we'll add 0, 1 to our stack. Everyone cool so far? Now we'll say, all right, we're starting at 0, 1. And so breaking down that wall was one function call. That's all we did. And then if we want to update again, we say, all right, what's at the top of our stack? Well, the current most element that we're looking at is 0, 1. Let's pick at random one of 0, 1's neighbors. Maybe we pick 1, 1 right here. Break down that wall and add 1, 1 to our stack so that it's the most recent thing that we're looking at. Okay? And that was one function call. And so visually, if you think about this as a program, we saw after the first function call, this wall break down. After the second call, this wall break down. And then in the next function call, we'll see another wall breakdown, and we'll see this process until the maze finishes. And so we'll go through this process just a little bit more quickly now that you guys sort of have the idea. Maybe from 1, 1, we go to 0, 1, break down that wall, say that we visited 0, 1. 0, 1 is where we're currently at. Maybe now we go to 0, 2, add that to our stack. From here, maybe we go to 0, 3, break down this wall, go to 0, 3. From 0, 3, maybe we go to 1, 3, break down that wall, so we're at 1, 3 here. From here, maybe we go to 2, 3, so break down this wall, go to 2, 3. And then from 2, 3, maybe we go up to 2, 2. Break down this wall, go up to 2, 2. From here, maybe we go to 2, 1, or 1, 2, my bad. 1, 2. We'll break down this wall, go to 1, 2. And here's where things get somewhat interesting, right? Because at 1, 2, we've already visited this cell, we've already visited this cell, we've already visited this cell, and we've already visited this cell. And so we're done with 1, 2. There's no more neighbors that we haven't visited with 1, 2. And so we'll say 1, 2 is finished. And so we'll recursively say, now what is the topmost thing on our stack? Well, it's 2, 2. Where are we at 2, 2? We're right here. And so we want to ask ourselves, can we go anywhere else? Do I have any more neighbors to visit? And the answer is yes. And so maybe we recursively go to 3, 2. And then from 3, 2, maybe we go down to 3, 3. And again, we've hit a dead end here, right? So if we go to 3, 3, every single one of our neighbors has already been visited. So we say we're done with 3, 3. We want to remove it. So what's at the top of our stack now? 3, 2 still. And so from 3, 2, we can go up here to 3, 1. So I'll start the list up here. 3, 1. From 3, 1, maybe I want to go to 2, 1. So I'll erase this and go to 2, 1. From 2, 1, maybe I want to erase this and go to 2, 0. And from 2, 0, maybe I go here to 3, 0. Now 3, 0 has all of its neighbors fulfilled. 2, 0 has all of its neighbors fulfilled or visited. 2, 1 has all of its neighbors fulfilled or visited. And we can keep going through this process, and we know every single neighbor has been visited. And so we'll just work our way up this stack saying, all right, we're done with each of these things until we get all the way back to the very beginning. And indeed, what you'll see is that we have created actually a somewhat more interesting maze from this 4x4 grid. All right. Did this process make sense to everybody? Everybody okay with this idea and how we were able to go through that step by step? All right, awesome. So the question is, how do we take this idea and turn it into code? And thankfully, it's not too difficult. We just have to think very carefully about how we want to visualize this process and how we want to do things like remove cells or remove walls in a way that scales up. Okay, so how do we want to think of this in terms of code? Well, we already know how we created a grid, and so we really do want to start out with a grid. Now, the thing that we didn't talk about is how we can remove walls within our grid. Remember, we talked in lecture 4 when we created Conway's Game of Life about how to create a grid of cells, but you can't like remove one of the walls of the squares of the cells when we're just visualizing this using squares. And so instead, what I propose that we do with our code is we've been thinking object-oriented throughout this course. And so what if our grid wasn't just composed of little squares, but instead it was composed of an object called a cell? And so now that we're thinking about this in terms of an object, we got to ask ourselves, what are the attributes that this object needs to have, and what are the functions that it needs to fulfill? And so a cell on our grid needs to have a position, and it needs to have a couple of other attributes. Namely, we want to know whether or not we've already visited a particular cell, right? That's really important in order for us to know if another cell needs to create, like break down a wall and move to it. And so we need to tell whether or not a cell has been visited. A cell also needs a particular length for a side. And I think that's all of the attributes that a cell needs. A cell also needs to have a function, right? It needs the ability to remove one of its walls. We start out with none of the walls removed, but we need the ability to remove a wall. And so maybe we have, maybe we actually think about this not in terms of a method, but in terms of an attribute. Maybe a cell has a north wall, which represents like the top. Maybe a cell also has an east wall, a south wall, and a west wall. And if the north wall exists, then we draw it. If the east wall exists, then we draw it. But maybe if the south wall doesn't exist, then we don't draw it, right? And so if we think about this in terms of how it might be displayed, if we're drawing the north wall, the east wall, the south wall, and the west wall, we have a full cell. But maybe if we want to remove a cell's north wall, then we just don't draw the line that would constitute that north wall. And we can tell whether or not a cell has a north wall using these 4 attributes. Maybe they're just like Boolean variables that tell us whether or not that wall exists. Is that idea okay with everyone? So we made the switch from thinking about the algorithm to the visualization to the object that will compose the visualization. And so the idea now is if we have this cell object, we have the ability to take a bunch of these cell objects, turn them into a grid. That gives us the ability to remove walls. And as long as we have the ability to access a cell and remove its wall, then there's nothing stopping us from taking this algorithm that we've created, this iterative algorithm a second ago, and turning that into a real thing that exists. So that's exactly what we will spend the rest of our time in lecture doing. All right. Any questions, comments, concerns before we start with our coding? Awesome. Okay. So let's go ahead and let me share my screen, and we can move over to our processing sketch. There we go. Okay, so like we just talked about, we're going to want an object called a cell, and so we need a new class for this cell. And we need a couple of attributes that this cell should have. The first thing that it should have is a position on our screen, an x and a y value. We know that we can represent this using a vector. We also said that it should have a size or a length, which we can represent as a floating point value. And then we also need to be able to tell if this is visited. And then finally, we said we would represent our walls using Boolean variables, north, east, south, and west. And each of these is true if that wall exists, if it hasn't been broken down, and it's false if that wall has been broken down. And so when we create this object, when we create the constructor for this object, we need to consider what information the cell object on its own won't have, what we need to pass into it. And so a cell doesn't know its position automatically within our grid, and so we'll need to pass in an initial position. And then the cell probably doesn't on its own know how big it needs to be, so we'll also need to pass in a length. Everything else, we know what the cell should start out with, and so we don't need to pass that information in. We can say our position is whatever initial position is given to us, and our length is whatever initial length is given to us via those parameters. Now, none of our cells start out as visited, so visited should always be false. And then we should start with all of our walls. None of them have been broken down yet. So our north, east, south, and west walls should all start out as true. Now, what we really want is the function for the cell to display itself. It should be void because we're not returning anything. So what we want is the ability for the cell to display itself. So the way that we would display ourselves if we were a cell is we would draw out each of those walls. So let's look at how that wall drawing might happen on our blackboard here. Okay, so if we're drawing a north wall, maybe we start out just thinking of this as a coordinate plane where this is 0. And we know we have a length variable being passed in. The north wall is going to run from 0, 0 all the way to 0 and our length, which I'll just call L. Right? And so our north wall is going to run there. Our east wall is going to run from our length, our length as the x and 0 as the y, so L comma 0, down to L comma L, right? Our south wall is going to run from 0 comma L to L comma L, and our west wall is going to run from 0, 0 down to 0, L. Right? And so, okay, this actually makes things quite easy on us because if we know that, then we know the coordinates that each line needs to be at. And so we can go back to our code and we can say, okay, if we want to display something, then let's think about everything in terms of starting at the origin, right? So regardless of what our position is at, we want to think about this in terms of starting at the origin. And so we already know how to do that a little bit from our lecture on fractal trees. We can translate our coordinate system from 0, 0 to our position.x value and our position.y value. So we've translated our entire coordinate system so that the origin is now at the position that this cell is at. And then we can say, if our north wall exists, then we want to draw a line, and this is exactly what we looked at on the board a second ago. We want to draw a line from 0, 0 all the way to length, 0. And then if our east wall exists, then we want to once again draw a line, this time from length, 0 down to length, length. If our south wall exists, then we want to draw a line from 0, length to length, length. And finally, if our west wall exists, then we're drawing a line from 0, 0 all the way down to 0, length. And that's it. If we want to remove one of the walls of our cell, we can just say cell.n for cell.north equals false, and then we won't draw that line. Does this process make sense to everyone? All right, so let's make sure that it works. So we want to create a 2D array of our cells, and these will compose a grid. And we need to have some sort of size for this grid, call it an n by n grid. We'll create our usual setup and draw functions. So we have setup there and draw there. And so maybe in setup, we just create a canvas that is a square, maybe 700 by 700. We want to define an n value. We want to define how big this grid is. So maybe we say this grid is just a 10 by 10 grid. We won't start it out too big. And so we know that grid is now a new 2D array of cells that is of size n by n. Now, we also need to, as you guys know, initialize this 2D array. So we looked at how to do that last lecture in Conway's game. We can just set up our double for loops as usual. So get that done here. And we even know exactly what we want to put in here because it's the same stuff that we put in for Conway's game in lecture 4. We want to say that the grid at cell ij is a new cell that has an initial position that is I divided by n, or I times 1.0 divided by n times our width. 1.0 here. And then j times 1.0 divided by n times our height here as our y, and then a size of 1 divided by n. This p vector should end here, right? This p vector takes 2 parameters, and then the second parameter for our cell is the size. So that's 1.0 divided by n times our width. If you guys are having trouble convincing yourselves of why this is the case, we go over the math for this in the last lecture, and that recording should be posted if it isn't already by tonight. Okay, so we've set up our grid. Now we actually want to be able to display our grid, make sure this thing works, and so we'll create maybe a new function that just says display grid, and all we'll do here is, can't type today, we'll use our double for loops to iterate over every single cell, and remember our cell has this display function, so we want to tell every single cell to display itself. So for every single row and column, let's go ahead and say that the cell at that column, the cell at position ij, needs to display itself. Let's go ahead and call that function in draw to make sure it works. And what we're expecting here is really just a grid of cells that has nothing special looking about them. Oh, right, okay. I pushed a matrix here, and I translated this position, and I never popped the matrix at the end, is my issue. Remember, every time we want to use push matrix, you also want to stop inducing that new coordinate plane upon our system. So we need pop matrix. And indeed, this gives us exactly what we're looking for. Now, we were able to do something that looked exactly like this in Conway's game with very, very few lines of code. But remember, the difference here is that we have the ability to tear down walls as we'd like. And that is going to give us a very nice way to create a scalable matrix. Okay, so our cells are done. I'll pause if there are any questions, and then we'll go into the real bulk of like the algorithm that we've been talking about. Okay, cool. So now that we have our cells in a grid, we need to figure out how to write this algorithm that we talked about on the board. So what do we need? Well, we said that we need a stack to keep track of all of our cells. And so this is going to be a stack of cells of everything that is in progress. I'll call this in prog. And we also need to import a couple of things from Java's util library. I'm going to import everything. That's bad practice. I'm importing a lot of stuff that I don't need. But just to keep it short, simple, and concise, I'll go ahead and do that here for now. And so I want to create a stack with all of these cells, and this will represent everything in progress. Now, I'm actually going to change this just a little bit. So when we were talking about how this algorithm works, we were thinking of this not really as a stack of cells, right? I wasn't writing down cells. I was writing down their position. And remember, if I have the position of a cell, if I have the x and y coordinates of that cell, I can access it very easily. So instead of putting cells inside of our stack, maybe we can put an integer array that has the x and y value, the row and column value, the I and j value of our cell within our grid. Is everybody cool with that idea? All right, perfect. So we need that stack, and so that stack of in progress is a new stack. And maybe we always want to start, we always want to say our start position for our maze is going to be just the cell 0, 0, the cell at indices 0, 0. And so maybe we can say in prog.push, and that's how you add something to the top of a stack, in prog.push, a new integer array 0, 0. And now we want to be able to update our grid, right? We want to be able to update our grid. And so how does this work? Well, we didn't talk about this explicitly, but if our stack is ever empty, right, that means that that means that we're done. We've like created our maze, because that means that every single cell has been pushed out of our stack because all of its neighbors have been visited. And so we can say at the very top, listen, if our stack of in progress elements is empty, then we'll return. We're done. We don't need to do anything else. However, if it's not empty, then we actually need to work with some element. And so we want to figure out what is the current element that we're looking at. That's going to be whatever is at the top of our stack. And so we'll say pop or remove whatever is at the top of our stack and set that to a variable called cur, because that's what we'll be working with. Now, cur is cool, but I actually want the x and y values. Those are going to be cur sub 0 and cur sub 1, because remember, that's how we push things onto our stack. We always did the x and y, row and column, I and j values of the cell. And so x and y are going to be cur sub 0 and cur sub 1 respectively. And now we want to say, all right, we want to randomly access one of the neighbors of the cell at xy. And we want to see if it's visited. If not, we want to go to it and then add it to our stack. Exactly what we did on the board. So how do we want to randomly choose a neighbor to visit? Well, it's not as simple as just generating a random number and then trying that, right? We want to try every single neighbor, but we want to try these neighbors in a random order. And so what we really want is a permutation of the neighbors. So if we say the northern neighbor is neighbor 1, or neighbor 0, the eastern is neighbor 1, southern is neighbor 2, and western is neighbor 3, then we want a permutation of the elements 0, 1, 2, 3. And that will give us the order in which to visit them. Everybody okay with this idea of permutations? Does everybody see why we can't use just random values? And conceivably you could, but you need to keep track of every neighbor that you have visited and make sure that your random number isn't the same. Like, you'd be doing a lot of repetitive cycles. So let's go ahead and maybe what we can do in order to do this is we know that each of our neighbors is going to be at a position that is at most 1 away from us, and we know where those positions are going to be. And so we can use the same process that we did in Conway's game to create a list of directions. And we know that those directions are going to be left, which is -1 in the x and 0 in the y, right, which is 1, 0, up, which is 0, -1, or down, which is 0, 1. And then we can say, all right, these are our different directions. They're going to represent a neighbor, and we want a permutation of these. And so this is going to be Java minutia. You don't need to worry too much about this, but collections, the collections like library, has a shuffle method where it creates a permutation of whatever you pass in as a list. Of course, this is an array, and so we want to pass it in as a list. The idea here is just that we're creating a permutation of this 2D array. And so this is going to create a random permutation of neighbors for us to visit. And now we want to go ahead and visit each of them. So we want to say for every single direction in our list of directions, we want to say, hey, what is this new neighbor's position? Well, it is our new x is going to be our current x plus whatever this directions x is, right? If we're moving left or right, that's -1 and 1. Otherwise, if we're moving up and down, it's going to be 0. So this is the current x plus the x value from the direction. And our new y value is going to be our current y plus the y value from our new direction. It's going to be these values right here. So nx and ny are the x and y positions of our neighboring cell. Okay, cool. So now what we want to do is we want to say, hey, have we visited this neighboring cell? Now, one important consideration, right? And we, again, had this exact same consideration when working with grids in Conway's game. And I guess the amount of times I'm saying the amount of connections that we have with Conway's game should sort of elucidate what we're going to be talking about next lecture, which is the amount of connections between all of this stuff. How if you understand just a little bit of it, you can do a lot with it. But what we talked about with Conway's game is that we not only need to check in Conway's game if our neighbor is alive or not, or in this case, if our neighbor is visited or not, but also are they in bounds? We want to make sure that we're not going out of bounds on our grid. And so we can, just like we did in Conway's game, do a quick check to make sure if new x and new y are within our grid. And we'll have to write this function in just a second. But if they are in our grid, and if they haven't been visited, if we haven't visited the cell at nx and ny, so we can write that out as this. If we haven't visited the neighboring cell, then we want to visit them and do stuff, right? And so we'll put a pin in doing that stuff for just a second while we write out this in function that makes sure that nx and ny are within our grid. And so in should return a Boolean, right? It should return true if our x and y positions are within our grid, and false otherwise. And so the way that we know if something is within our grid is if our x position is greater than or equal to index 0 and less than index n, which is the length of the grid, and our y index is greater than or equal to 0, and our y index is less than n. Okay. Everybody following me so far? All good? Cool. Okay. So now that we've done that, we actually want to go through with our algorithm. So if we have not visited this cell, then we want to say, all right, hold on. We need to add you to the list of in progress cells. And so this part might get just a tad confusing. Not only do we want to add this new cell that we are about to visit into our list of in progress cells to visit, but the fact that there was one neighbor, at least one neighbor, that wasn't visited tells us that, hey, there might be more neighbors of the current cell that we're on that might need to be considered. And so we need to make sure that the current cell that we're on is still an in-progress element. Just because we've seen the north side, just because we've broken into the north neighbor and he was unvisited, doesn't mean our east neighbor has been visited. And so this element that we're currently on needs to remain in progress. So we'll add to our list of in-progress elements our current element, and we'll add the element, this neighbor that we have just visited. And so that we know has the positions new x and new y. Okay, so that marks the visited process. Now we need to actually break down the wall between the neighbor and our current position. So how do we want to do that? Well, the wall that we break down is a function of where this neighbor is relative to our current position, right? And so if the direction sub 0 equals -1, then that means this neighbor is to the left of us, right? Their x position is 1 less than ours, so they're to the left of us. And if this is the case, then we need to break down our western wall, and they need to break down their eastern wall, right? So we want to say the grid at xy, that's our position, our west wall needs to be broken down, and their east wall needs to be broken down. Now, if their x direction is 1, that means they're to the right of us, right? And if they're to the right of us, then we need to break down our eastern wall, and they need to break down their western wall. Everybody cool with that idea? Cool. Okay, we'll repeat this process. Whoops, this should be 0. We'll repeat this process for the up and down cases. So if they are above us, if their y is -1, if they are above us, then we need to break down our northern wall, and they need to break down their southern wall. And then finally, if their direction is 1, they're beneath us, and so they need to break down their northern wall, while we need to break down our southern wall. So we break down our southern, they break down their northern. All right, we're almost done. I missed one quick thing, and it is very small. Basically, every time we want to update our grid, we want to say that the current position that we're at, right, the current cell that we're at, that we're actually operating on, has been visited. We've done stuff with it. We've seen it, and so we want to say it has been visited. All right, everybody okay with everything so far? Do we have a syntax error somewhere? We might, but we'll see about that maybe when we get there. Yeah, we'll see about that when we get there. Okay, so now that we want to draw, we not only want to display our grid, but we also want to update our grid. And we want to clear our background between each of these calls. So maybe we get a syntax error here. It is getting mad at me. Yeah. Okay, maybe I just have an extra semicolon or something? I do. Okay, so yeah. I started this if statement and I never closed it. So I think it is happy with me now. Let's go ahead and run this thing. Okay, okay, this is not working. Let's take a look at Y. I wonder what's happening here. So we want to say, maybe I messed up my bracket somewhere and that's what is messing me up here. Here, let's make sure everything is in line there. Okay, so we want to say whenever we update that our current position has been visited. And then we shuffle our list of directions. We go ahead and create our new direction. And then we want to say if this thing is in and it hasn't been visited, then we add it to our list of in progress things to visit. Oh, you know what? I think what I need to do is mark this new position as visited down here. So if we're here, then we want to say that the grid at this new position has been visited. Let's see if that, no, it didn't like that. Oh, because I put it within the wrong place. So that should be within our if statement, right? We only want to visit it if it hasn't already been visited, and if it's in, then we want it to be in our visited list. Okay. And it looks like that is fixing our maze. All right, so we just saw our maze. Ooh. Everybody can still see my screen okay? All right. Yeah, my HDMI cable was not fully within the computer. Okay, so yeah, we created a maze. The reason that we want to put our visited down here is the same reason that we actually added this to our visited in the algorithm when we drew it out on the blackboard, right? The reasoning is we want to visit that cell as soon as we add it, not all the way up here. Okay, so let's make sure this this thing works. Let's go ahead and run that just once more. Okay, so we're generating a maze, and this should be pretty exciting on its own. Like, it is actively creating a maze in front of us in real time, which is super awesome. Now let's mess with a few parameters, make this a little bit more visually appealing, and then talk about some of the shortcomings of this approach. So the first thing that I want to do, just for fun, is up the N, make this just a little bit bigger. So yeah, this totally still seems to be working. Looks like we are backtracking away. The problem that I'm having is it would be really nice to be able to keep track of where I currently am. My eyes are kind of darting around the screen right now looking for exactly where I'm removing from and where I am. So it might be nice to be able to visually figure out where that is. So how do we want to do that? Well, we know where we currently are, right? We know which cell we are operating on because it's the cell that is at the very top of our in progress list. That's what we do stuff with. And so maybe what we want to do is in our cells display method is create the ability to draw a square and color that square in. And maybe the only time we color in a cell is when it's the current in progress cell, right? Because that's the one that we're making modifications on, and that's the one that will be removing barriers or walls between it and other cells. And so maybe the way that we want to do this is we just want to draw a square. Now, the reason we didn't want to draw a square earlier was because squares, we can't remove their individual sides. But if we just draw a square that has no stroke, it has no outline, then we can go ahead and put in a square at our X position and our Y position with our length, pos.y. And And then we want to shift our stroke back to 255 because our stroke is what makes our lines visible, right? And so maybe just to test to see if this works, we can go ahead and fill this with maybe the color red. And so I think what we should see here is the entire process happening, but with a red background. And we can go ahead and modify that. Whoa, okay. That is not entirely working as intended. Why is that? So we have a square at position X, position Y. Here, let me get rid of this no stroke. Oh, because stroke 255 makes the stroke white and not black. I need a black stroke. Okay, this looks a lot closer to what we had in mind. So it is actually filling in each of our cells with red. And so maybe what we want to do, right, we don't want every single cell to be filled in with red. What we want is just the cell that we're focusing on, just the cell that we're operating on to be filled with red. And so we want that to move around and do its thing. And so maybe what we say is when we display our grid, maybe we can figure out what the current cell is. And remember, we knew exactly how to do that up here. We said the current cell is whatever is at the top of our in progress stack, and we can get its X and Y values. And so maybe we can say, listen, if I is equal to X and J is equal to Y, that means that the current cell that we're looking at in these double for loops is the same as the current cell that we're operating on within our update grid function. And if that's the case, let's set our fill color to be red. And otherwise, we'll just say there's no fill at all. So let's see what happens when we run that. Oh, didn't like that. Okay, yeah, actually, so the reason that it didn't like this is because there is a point where our stack becomes empty, right? And we were able to solve for that in update grid by saying if the stack is empty, then we're just going to return. So here, we can't just say if the stack is empty, then return, because then we won't actually display our grid. And so maybe the way that we get around this, right, is we want to say, all right, let's display our grid, let's update our grid, and then let's say if our in progress stack is empty, then we just won't loop anymore. We won't go through this draw loop anymore, and the way that we do that in processing is just by saying no loop. So if we run that again, it's not running. I wonder why. In progress should not be empty. Oh, right. Okay, so we don't want to pop anything from our display grid. So the way that this is working is it's saying cur is remove whatever is at the top of our list of in-progress elements, which we did want to update our grid, but we don't want when we display it, right? Why would we want to remove something when we're displaying? Well, we wouldn't. And so the way that we can just look at what the topmost element of a stack is without actually removing it is with the peek method. And so if we do that, okay, this is kind of working. Our square is not where we expect it to be, but we do have a square and it was moving around and it still is moving around and it looks to be catching up, and that looks to be somewhat right in the latter half of our code there. Okay, so our square somewhere is going just a little bit wrong. Why could that be the case? Let's see. We do want to say that there is a square at our X position and our Y position. Oh, right, okay. We don't want to say our square is at our X position and our Y position because we've translated, remember, our entire matrix so that the origin is at our X position and our Y position. So we want this square to be at the 0 values and not at the positional values. Okay, that makes a little bit more sense. Let's go ahead and run that now. And okay, that looks a lot cleaner. here we are definitely drawing out a maze. Awesome. All right, and so what you'll see is that this will eventually backtrack its way all the way to the beginning, and indeed it does. We're hitting an empty stack exception here because we call display grid at the very top before we do update grid, because I commented this out. So let's go ahead and put that back in. And so this should run without any errors or exceptions this time, at least fingers crossed, let's hope. I don't want to say anything before the animation ends, but I predict that it will run without any exceptions here. And indeed it does. And that's exactly what happens. Cool, awesome. So this is maze generation. It's a relatively straightforward process. It was just a little bit difficult to convert what was naturally a recursive process into an iterative one. But once we were able to figure that out, the code for all of this really wasn't that hard, nor was it very long. We wrote about 80 lines here and very few here. We wrote like 30 lines here. And a lot of that was really just setting stuff up, really, really basic stuff. Okay, so maybe just for fun, we go ahead and increase this size to something like 80. I'll go ahead and let that run while I talk to you guys a little bit about the end of this lecture and what we'll be talking about on Friday. So we covered maze generation and not maze solving, but as you might be able to guess or expect, the way that we want to solve a maze is very similar to the way that we want to generate this maze, except almost in reverse. We can use a recursive DFS, a randomized DFS, a backtracking approach in order to solve the exact same maze that we've created by waiting, like going in a direction until we hit a wall and then backtracking our steps recursively, perhaps, until we have a new direction that we can go in, and then trying that new direction. That is probably like the most naive way, one of the most naive ways of solving our maze. There are lots and lots of like way more complicated, way more interesting ways to solve a maze, but that approach will require very little modification to the ideas and concepts that we've talked about today. And so I'll go ahead and include that as a problem on the assignment for this lecture. But it should be relatively straightforward. Now, there's also lots of very fun what-ifs that we can deal with when creating mazes. The first big one that you might consider is mazes that aren't squares, perhaps hexagonal or octagonal mazes. Those are a lot of fun to play with, and I have the code for some of those that I've written if any of you guys are interested in looking at something like that. The other thing that you might consider is what would happen if we looked at 8 directional neighbors instead of just 4 directional neighbors. And of course, that is a very easy thing to tinker with. You can do that using the Conway's Game of Life code because we looked at 8 directional neighbors there just last lecture. I think that would probably take you like between 2 and 5 minutes to make that change. And of course, as always, there's all sorts of fun and interesting ways to color our mazes and, you know, mess with those types of parameters. Now, what you might recognize is that this maze, while it certainly, is maze-like and has all of the qualities of the perfect mazes that we've talked about, doesn't have a defined start point and end point. Or, I mean, it has like a defined start point, and we know where that is. It's 0, 0 because we made it so. You can totally randomize that to be any start point within any one of the boundaries. But what's a little bit more concerning is we don't know exactly where the end point is. And that is going to be super easy to calculate. It's just whenever the first time we hit the edge of like whichever edge of this window you want the exit to be on, that will be your exit for the maze. And we haven't like defined that using color or using any sort of indicator here. We totally could because it's I think maybe like 5 or 6 lines of code. But I did want to point that out to you guys if that's something else that you want to play with. All right, awesome. Well, that is it, guys. That concludes all of the coding that we're going to be doing for lecture. I really appreciate you guys sticking with a lot of the coding. I know we had to do a little bit of debugging here and there. We had to do a lot of blackboarding. And I'm really hoping that you guys maybe have a better sense of how to work with processing now, some of the tools to work with processing. And like I said, we'll talk about all of that stuff in a little bit more detail on Friday. So it looks like we're almost done with this maze. I'll go ahead and let it play through the end, but that is the official end of lecture. Thank you guys so much for coming, and I will see you guys for a very short session, maybe like 30, 45 minutes on Friday, same place, same time. But yeah, awesome. Thanks everyone.